Now let us try to understand channel model for multiple sources. I have assumed an earlier case was single source. Now let me try to explain for impulse channel model for multiple sources. So before that, let me again draw the line, draw the room which has multiple sources. So assume that there are many sources. So this is a Ti, this is a Ti plus 1, and this is a Ti minus 1. And then there is a receiver here, which is a Rj. And this receiver has, as earlier, has some cone where it can accept light. And so there will be a direct light falling. So let me show this is the radiation pattern of the source, and this is the normal, this is the normal, and the light is falling from here and getting collected here. And also we have seen that there can be reflected light also from this point. So this is for a single source. This we have studied and we have named different angles. So you can refer the previous diagram for clarity on the different angles. And then also there is a contribution from Ti plus 1, both line of sight as well as non-line of sight. So let me draw a non-line of sight here. So light from Ti plus 1 gets reflected from the wall and it's collected here. And suppose this is K minus 1 reflection, then it will have impulse response Hk minus 1. This is function of T, and this is coming from Ti plus 1 and Rj. Oh, sorry, this will be, because there's a small area here, because this now acts as a transmitter for this Rj, so this will be sigma R. Or let me write this as epsilon R. And this is for I plus 1 transmitter. So this can be N, where N could be, in this case it is I plus 1. Otherwise N can vary depending upon the number of sources you have at the top. So if I try to write channel model for such a case, this is multiple case, but there is only one receiver. So this can be written as, for the line of sight, HS0 T of say source Ti Rj as before. So this is your visibility factor depending upon the blockage, either 0 or 1. And ARI is the collection area. This is related to the radiation, the source radiation pattern. These the angles which are mentioned here, phi ij and theta ij, you can refer to the earlier diagram. So, and this distance is 2 pi dij square. So this I'm referring this as. This is for one source Ti. Similarly, you will have for Ti minus 1 and Ti plus 1 and whatever number of sources you have. So cos theta ij, and this is a rectangular function theta ij theta c, depending whether the light is falling within the cone. And then as we know that these are line of sight, they are all Dirac delta functions. So this is represented here delta, T minus Dij is the distance. This is Dij. Dij divided by C. This rectangular function, again rewritten here. So if I calculate for k bounds, the way I had done for the earlier case, that will be given as convolution of k minus n, k minus 1 bounds involved with HS0. And this is for every Tj, there is only one Rj. So, and that is why you see the summation here. So this actually tells you the number of sources. So right now it is assumed that there are m sources. So this is n is equal to 1 to m, and this is the coefficient here, and this is the area of the wall, area on the wall, which if you are considering n is equal to 1 or n is equal to 2, or depending upon which source you are considering, and then you have to convolve k minus 1 of the reflection point with the direct coming from the source, which is a reflection point for one ray, but becomes a source when it is collected by the receiver. So this is given by d epsilon Tn. So let me again refer. This n tells you the index of the source, and this is actually we was acting as a transmitter now. So this is T area, that small area on the wall. So the overall CIR will include both the contribution coming from different sources, which is captured by this summation, and the k bounces, which is captured by this summation, and this k tend to infinity. So this is the overall response. But as explained earlier, k is equal to infinity, this value will be 0. The contribution of the to the impulse response will be, to the overall impulse response, channel impulse response will be 0. So it is only limited up to n. So that is why it is written as n, and n, as discussed earlier, is between 3. So this becomes a channel response, for overall channel response for the system which has multiple sources and single receiver, which is summation I is equal to 0 to m. M is number of sources. Summation k is equal to 0 to n, where n is the reflection. One can take the value of 3. So up to 3 reflections, there will be some contribution to the channel impulse response. Beyond 3, it is negligible. But if you want to have some accurate value of channel impulse response, one can go up to 10. And HIK is of the kth reflection from Ti to Rj. So this is the overall channel response for multiple sources and single receiver. Similarly, one can do for multiple sources and multiple receivers. So again, there will be one more summation term, which will be actually corresponding to number of receivers. So this is how you do recursive method for modeling the channel. There are some other methods also. In the beginning, we had discussed, deterministic methods and non-deterministic method. So far we have discussed the deterministic method. So let us discuss some methods which are non-deterministic. So ceiling bounds method is one of them. So in ceiling bounds method, this impulse response is a function of t, of course, and it's also a function of a. I'll just define what is this a. So this is S0, channel optical wireless channel transfer function, 6a raised to power 6 divided by t plus a raised to power 7, and this is the unit function. Where a is given by SC. This SC is the height, the distance between the transmitter and the receiver, and C is the velocity of light. And if I calculate the RMS value of the delay spread, this is a multiplication of RMS delay spread and channel transfer function which is a function of t and a, is given by empirical formula a by 12 root 13 by 11. And if I calculate the 3 dB bandwidth, it is actually given by 0.925 divided by 4 pi drms. So this is also a fairly accurate model which is used, generally used. And this is a faster way of, finding out the channel model, but it may not be as accurate as a recursive model. And it may not have, flexibility, but this has been computed for two types of scenario where the value of A is different when you have, there is no blockages or no shadow, and there's no, blockages coming inside the room. So under those cases, A unshadowed value is not 2SC by C, is given by this formula. And similarly, A shadowed when you have blockages is given by this formula. And here S is actually, suppose this is your transmitters at the ceiling, and this is your receiver. So this will have some distance, and there is a diagonal distance here. So this distance is, say, for example, D, and this distance is, say, P, and this S actually is defined as a ratio of this horizontal distance, D, over the diagonal distance. So this is another formula which one can use for finding the bandwidth of the channel or the impulse response of the channel by using this formula and this expression. Where H1T, forgot to mention, is actually one bounce impulse response. The other model which can be used is integrating spherical model. So in this case, there are two components. One is line of sight. So this is represented as Dirac delta pulses. This is as usual, so there's no change here, Dirac delta pulses. As we have discussed earlier. And here in this, I have assumed TS theta and G theta, they are equivalent to 1. So it is a rather simpler expression. Lambert-Eaton pattern and cos m phi, cos theta, and Dirac delta pulses. So there's no change as far as LOS channel model is concerned. But for the diffuse case, it is assumed that this impulse response for the diffuse case can be represented as an exponential function, where H, this is the diffused case for optical wireless transfer function, divided by, this is tau. So let me, sorry for this mistake, this is tau. So H diffuse divided by tau into e raised to power minus e by t tau, where tau is the time when the ray almost dies or it is not collected by the receiver. So how do you calculate to find out the impulse response for the diffuse case? We need to find out this H diffuse. So H diffused, if I assume, this is based on a spherical model. So if I assume there is a sphere, and so this is a center, and there is some area dA1, for example, and then some area dA2. So how much light is collected by dA2 from this dA1? I'm just trying to calculate from dA1. Similarly, you can integrate over the whole sphere and find out how much light is collected by dA2. So if I, suppose this distance is d, and this is with the center, so this is a theta1, this is theta2, and this is, say, the radius of the sphere. So the H diffused will be m plus 1 2 pi d square. Now I want to find out what is the light which is falling onto the dA2. So this is the radiation pattern, and then it is governed by cos theta 1 and cos theta 2. So this is the expression for H diffuse, and this can be written as, suppose I assume m is equal to 1 for simplicity, and already I have assumed, this has 1. So this is simplified, dA2 by pi d square cos phi, because m is equal to 1, cos theta 1 into cos theta 2. Or it can be written as dA2, this area, dA2 pi d square cos phi, because cos theta 1 is equal to cos theta 2, because if you see here, d is 2r cos theta 1, and this is 2r cos theta 2. So basically cos theta 1 is equal to cos theta 2. And if I put in this expression, this is what I get. dA2 pi d square cos phi into cos square theta 1. And this I can put in the expression, the earlier expression of, let me show you that expression. I can put in this area, in this expression here, and also replace the value of d, and this is cos square theta 1. This we have seen, cos theta 1 is equal to cos theta 2, and put the expression of for d, then what you get is dA2 cos phi cos square theta 1 divided by pi, this is d actually, 2r cos theta 1, this is d. And if you do some calculations, so this will be dA2 4 pi r square. So this becomes dA2 4 pi r square. Now considering reflectivity, because I have not considered the reflectivity part, that is, say rho is the reflection coefficient, then this expression will get modified as dA2 into a reflectivity part, and this is 4 pi r square, which is the total area of the sphere, into average reflectivity from different parts in the room, whereas the average reflectivity is defined by the total area of the room into sum of those small areas multiplied by reflectivity for that particular area. So this is how average reflectivity is defined. And if you calculate the F3 dB part, this is 1 by 2 pi f tau. The tau is the time when the ray almost dies. So that time is referred as tau. I mean, it is not getting collected by the receiver. The value or the power intensity after getting so much reflection is so low that there's no significant contribution. So this is how you define tau. And this 3 dB bandwidth is actually a function of this tau. So 1 by 2 pi f tau. So just to understand this value of tau, so if your rho is high, that means it is getting reflected from the walls and it will suffer more reflections. And this tau will increase actually before the ray is insignificant. So once this tau increases, and then if you increase the tau here, this F3 dB will go down. So this is a low channel, a low bandwidth channel. On the other case, if the value of reflectivity is low, that means the light is, if it is low, then the tau value actually decreases, and F3 dB increases. So this is a case of high bandwidth channel. All right, so depending upon the value of reflection coefficient, one can, find out or estimate the value of tau. And then as this tau depends on this 3 dB bandwidth, one can find out the bandwidth of the channel, whether it is a low bandwidth channel or a high bandwidth channel. So let us now understand what are the steps involved when you model a channel using recursive technique. So what normally is done, the environment will have some objects. So you should have some, you should know how to model those objects. And also you should also have what kind of reflection is there on the wall, reflection. The value and the type. Also, one should know what is the radiation pattern. And also of the transmitter. Also, one should have detector specifications. What is FOV? What is the concentrator gain? What is the preamplifier if one is using preamplifier in the receiver? So all these things should be known, and you should be able to model these objects, and all these values are known, and they are actually the inputs to a 3D indoor environment modeling. Software. So one of the software which is normally, or which is popularly known as used, is GMAX. So they become input to this GMAX, and then you can model your room, which is 3D environment modeling. And once you have done this, then you can use ray tracing. And this ray tracing can be sequential, can be non-sequential, or some random tracing using Monte Carlo, random ray tracing. So one can use, different types. And then once you have done this ray tracing using one of these methods, and then the data is imported to MATLAB, for example, and you are able to, model the channel. So this is what you get is channel impulse response or modeling the channel. So this is how, when you want to model a particular channel, so these are the different steps which are involved, because each environment may have different type of setup. For example, there's a factory or an office environment, or for a hospital, for example. So all these input conditions may be different, and similarly you will have different channel impulse response. So depending upon the environment, you design your system, or you find out your channel impulse response. So these are some of the examples. How does a channel impulse response look like, and what insight can it give? So this is what I have considered here is a room which has got, say, 4 LEDs, S1, S2, S3 and S4. And S4, for example, has some dimension 0.6 to 0.6, and each LED has actually is an array. It is not a single LED. So there are many LEDs. Or for example, here it is 10 cross 10 LED chips shown here. So this is one transmitter having, or one LED, which is array and which consists of 10 cross 10 LEDs. And receiver is say somewhere here. And if you see the transmitter pattern or the Lambertian pattern, radiation pattern of the device, which is something like this. This is emission pattern of the source. So you can find out the value of M from here, and you can find out the value of half irradiance of the, because there is some intensity here. This intensity falls say half at this point. So this angle will give you half irradiance, and similarly half this side. So, and from there you can calculate the value of Lambertian parameter. And if you see the impulse response for such a kind of scenario, then suppose your receiver is here, it is close to S1. So you see a peak there. This is because of S1. And the contribution from other LEDs, S2, S3, S4 is minimum. So you see, for example, this could be contribution from S2, say. This is S1, this S2, and this could be, for example, this contribution can be from S4, and probably S3 is too far. It is not able to, is not contributing to the detector, so you don't see any peak here. So this is corresponding to, only line of sight, or K is equal to 0. Channel impulse response, and from here you can find out in terms of time what is the bandwidth if you're considering only line of sight. Now, if you see include the first order reflection also, then there will be contribution, which you see here. This is a contribution which is coming from first order reflections. So, for example, because it is traveling a longer path, the first order reflection, because it may come, it can strike here and then go to here. So this may be a longer path as compared to the line of sight path. So it is coming at a later time. That is why you can see this coming beyond 10 or 15 millisecond, whereas the line of sight was coming in 10 millisecond. So, and this is magnified here. So this is the contribution of the first order reflection. And if I combine both the line of sight and the non-line of sight, considering only first order, one reflection, then what you get is, this is because of the source which is closest to the receiver, some other source, third source, and this is a contribution from non-line of sight. So these are the LOS components from different sources, line of sight component from different sources. LOS, for example, this was 1, or this was 2, this was 3, and then maybe nothing from LO from the 4. So this is how you can find out, from this trace, you can find out what is the bandwidth of the, once you know about the channel impulse response, then you know what is the bandwidth of the channel. So we will stop at this point. This was a discussion about indoor channel modeling, where we had used only single source and single receiver, and also we had used multi-source. But now specifically we will try to understand a MIMO channel where there are multiple sources and multiple receivers. How do you represent a channel for a MIMO system? Thank you.